Hello. The topic of this video is equilibrium of isotopes. And let me just explain what I mean by that. So last video we talked about a radioactive isotope decaying into its daughter products. And there's a simple mathematical formula for that, exponential decay with a half-life. And you could understand that pretty clearly. Unfortunately, things are often not that simple. You have one radioactive isotope decaying into another isotope, which then decays into another isotope, and it sets up sort of a chain of reactions that over time comes into equilibrium. So you have the parent and the daughter coming into equilibrium. And so that's the topic of this video. And we're going to go over the mathematics that describe that, of this equilibrium process of isotopes. So fasten your seatbelts. Won't be that bad. Here we go. So I'm going to start here with a parent isotope in red. And it's decaying into some daughter isotope in blue. And the daughter isotope itself further decays down into another isotope, and the chain continues. You can have many of these. So a classic example of this is the decay of radium. So we start here with radium-226, and that decays. It decays by alpha decay. It decays into radon-222, and then plus an alpha particle. And then radon itself decays down into polonium-218. That's again an alpha decay. Look here, you can see the number of nucleons is going down by 4, of course. And then let's look at the half-lives for each of these decays. So the first one for radium is very long. It's 1,622 years. And then the half-life for this decay is very short, 3.8 days. So now let's look at this graphically. So activity versus time. For the parent isotope radium, it's decaying exponentially, but the half-life is very long. So it's a roughly constant activity over time. And now let's look at the daughter isotope. At first, there's no daughter isotope, so the activity is 0. So it starts at 0. But then it starts to build up over time as the parent decays. So it climbs up, and it eventually reaches up to the activity of the parent isotope. So the activity here of the daughter is equal to the activity of the parent. This kind of equilibrium is called secular equilibrium. And it happens when the half-life of the parent isotope is much, much longer than the daughter isotope. There's another kind of equilibrium that can happen when the half-life of the parent isotope is just a little bit longer than the half-life of the daughter isotope. A classic example of that is molybdenum-99 decaying into technetium, and I'm going to draw that quickly. So 99 molybdenum, it decays down via beta emission into technetium-99. And this is a metastable state of technetium, which means it's an excited state in the nucleus. So that can decay down into the ground state of technetium-99 through internal conversion. You remember that decay scheme? And technetium-99 further decays down into ruthenium-99, which I'm not going to worry about at this point. But that's via beta minus decay. And then just for completeness, the molybdenum can decay directly into the ground state of technetium, and it happens 12% of the time, but most of the time it happens to decay down into the excited state of technetium. So let's look at the half-lives of these. The first part, it's 66 hours. And the decay of technetium down to its ground state happens with a half-life of 6 hours. So here you have a situation where the half-life of the parent isotope is a little bit longer than the half-life of the daughter isotope. So if I were to draw the decay scheme here, the activity curve, the parent isotope is now decaying with some visible decay curve, like you can see here. And the daughter isotope again starts at nothing, but builds up, and eventually reaches some equilibrium with the parent. And you can show here that the activity of the daughter is larger than the activity of the parent isotope. And I'll skip the math, but here's the formula for the relation of these two. It's a ratio of decay constant. And at long times, this is the formula for the activities. You can also write it in terms of half-lives, and here's the formula for that. You can show that these two are equivalent.
So we might look at the limiting case where the half-life of the daughter is much less than the half-life of the parent. In that case, this whole ratio in the bottom equation here becomes 1, essentially, equal to 1. So in that case, the activity of the daughter is equal to the activity of the parent, and that's the limiting case of secular equilibrium. Now, everything I just described here in the bottom is transient equilibrium. And you might wonder what happens when the half-life of the daughter is more than the half-life of the parent. In that case, you can't have equilibrium, and so it's not useful to us medically.
So at this point, you have all the basic tools you need to understand radioactive decay. I encourage you to really go and do some problems. I think that's the way to understand these concepts and to get them firmly in your mind. And that's actually true of all the physics that you're going to learn in these videos. Problem solving is probably the key. I'm going to leave you with some extra reading. In particular, the treatment of Pogorsak is really elegant. It really elegantly describes the mathematical formulas behind this. And so if you're interested in that, I encourage you to read it. And we'll continue on in the next lecture. We're going to move on to some practical applications of what you've just learned. And you'll see really quickly how this comes into use with patients. Thanks.